Okay, so this lesson will look at discrete probability distributions. And you have this sheet, and you can pause the video if you want to look over all these examples up at the top here. Okay, so you can pause that, and I'm going to go right down to the bottom. And what I will say is that when you look at discrete compared to continuous, it's important here to look at distinguishing between the two different random variables, discrete and continuous. If you think about putting the outcomes on a number line, a discrete random variable has a countable number of outcomes, like 0, 1, 2, 3. A continuous random variable, like time it takes to climb a flight of stairs, weights, heights of things. Okay, when you think about putting those on a number line, you could have like 0, 0.1, 0.01, 1.24. Okay, so there's an infinite number of possibilities, or an uncountable number of outcomes. Okay, so we're going to go right down to the bottom of the page. And again, if you need to pause the video and look at the examples on top, go ahead. Okay, and what we're going to do is we're going to look at a discrete probability distribution. And all that is, it's a list or table of every possible value of the random variable with its corresponding probability. The probability may be relative frequency, theoretical, or subjective. So a very basic example is if you roll a fair six-sided die, let random variable x represent the number of dots showing. In part A, we want to construct a probability distribution for x. Okay, so a probability distribution for the number of dots showing, and then we're going to graph that distribution. Okay, it's a very, very simple thing to do. We have the number of dots, okay, which is going to be your random variable x. And then we're going to have p of x, which is the probability of getting x number of dots. Well, when you roll a fair six-sided die, the possibilities for x, or the number of dots, are 1 through 6. Okay, now what's the probability that if you roll a die you get a 1? Well, p of 1 is 1/6. Okay, so p of 1 is 1/6. Rolling a 2 is 1/6. Okay, and in fact, the probability of each individual outcome here is 1/6. Okay, so they're all 1/6. Okay, and that's all it is. Okay, it's very, very easy to do, very basic, especially with this example. Okay, the next thing we're going to do in part B is we're going to look at graphing the distribution. Well, when you look at graphing this, okay, if you were to graph this, you want the total number of possibilities, or the number of possibilities for your random variable x across the bottom. Well, we could have had 1 dot, 2 dot, 3 dots, and so on. And then p of x, the probability of x number of dots, will be up the side. Well, in this one, all the probabilities are 1/6. So that means I'll just put a random tick mark here at 1/6. And then all the bars will have the same height. Okay, so when you make this, okay, every bar is going to have the same height. Okay, so that would be what your distribution looks like on a graph. Okay, again, very basic. Okay, if these were different probabilities, then you would have to use a different scale so they all fit on the p of x axis. And how would you classify this distribution? Well, that means, are we looking at a normal distribution? Is it uniform? Is it skewed left, skewed right? Well, all the values are the same here at 1/6, so that is a uniform distribution. Okay, so the name of that distribution would be a uniform. Okay, so hopefully you see that's pretty basic. Okay, not too crazy yet. Okay, so if we go to the next page, okay, some things you definitely need to know when looking at a discrete probability distribution. Okay, number 1, the sum of p of x equals 1. So all that means is when you add up all the probabilities of each event, they add up to 1. On the previous example, p of 1 was 1/6, p of 2 was 1/6, p of 3 was 1/6, and so on. When you add all those 1/6 together, there's 6 of them, so they'll add up to 1. So that represents all the possible outcomes. The second thing Was that 0 less than or equal to p of x less than or equal to 1? That's a fancy math way of just saying that each individual probability has to be between 0 and 1. Okay, and it could be 0, could be 1. Okay, that's where the equals to comes in. So when you look at 1/6, okay, 1/6 is between 0 and 1. Okay, a third thing, the mean, mu, equals the sum of x times p of x. Well, x, in the previous example, was the number of dots. P of x was the probability of the number of dots in each of those cases. Okay, so when you add x times p of x, and we'll get to an example of that here, down here in this table. Okay, we'll get to that here in a minute, so it'll make more sense. But the question, one question is, why do we use mu rather than x bar? Okay, so when we look at this question here, why do we use mu rather than x bar? Well, mu, remember, is the population mean, and x bar is the sample mean. Well, when we look at a probability distribution, we have all the possible outcomes, so that means we have the population of possible outcomes, not just a sample. So that's why we use mu instead of x bar. Okay, the variance, again, it looks very confusing, but you take the sum of x minus mu squared, so you're going to take each individual x value, subtract the mean from it, square that, and then multiply it by the probability of each of the x values. And again, this example down here, I have a table. We'll go through that together. And then the standard deviation is always the square root of the variance. So sigma equals the square root of sigma squared. So once you find the variance, you take the square root, and that'll give you the standard deviation. Okay, so example number 2. A survey is given, and the people are asked how many credit cards they carry. Let random variable x represent the number of credit cards. The probability distribution is given. Okay, so when you look at these x values, they represent the number of credit cards that somebody carries. So the only possibilities in this population we had were 0, 1, 2, or 3. The probability someone has 0 credit cards is 0.1. The probability someone has 1 credit card is 0.3, and so on. Okay, so what we're going to do is we're going to find the mean, the variance, and the standard deviation by using this table. Okay, and filling in this table is going to take care of all these symbols up here. Okay, so hopefully it won't be quite as confusing. So when you look at x times p of x, okay, what we look at is, for the first row, we have 0 times 0.1. Well, 0 times 0.1 is 0. 1 times 0.3 is 0.3. 2 times 0.4 is 0.8. And then 3 times 0.2 is 0.6. Okay, so that's x times p of x. Now, before we do x minus mu, we have to know what mu is. And if we go back up here, mu is the sum of x times p of x. So you take that column that we just did and add them together. So the sum of x times p of x equals 1.7. Okay, so the mean is 1.7. Okay, so I'll say mu equals that. Okay, so when you go through and subtract x minus mu, you're going to take x in the first row, which is 0, subtract 1.7, which is negative 1.7. Now, I suggest to go right across the row, because if you have to use a calculator, you can do these calculations a lot easier now. There's a little misprint here. This 2, that should be squared up here. And if we look at the formula up here, x minus mu squared, something happened with my formatting on that. My row, my column isn't wide enough. Okay, so that's x minus mu squared. So you're going to take negative 1.7 and square it. That'll give you 2.89. And then you're going to take that 2.89, which is x minus mu squared, multiply it by p of x. Well, p of x in the first row was 0.1. So we're going to take 2.89 times 0.1 and get 0.289. Okay, then the next row, we have x minus mu, which is going to be 1 minus 1.7, which is negative 0.7. Square that to get positive 0.49, and then multiply that by p of x, which is 0.3 in this case. So 0.49 times 0.3 is 0.147. Okay, and you go across and finish off each row, And I already have it done here, so I'm just going to skip right to that. Okay, so here is the table when you finish it. Okay, so next thing we look at is to graph the probability distribution for x. So notice our x values are 0, 1, 2, 3, so that'll go across the bottom as random variable x. And then up the side we have probabilities of 0.1, 0.3, 0.4, and 0.2. So if you make a little scale of 0.1 going up the side, okay, and I have it done here, so I'll just show you to save time. Okay, again, we put our random variable x across the bottom, 0, 1, 2, 3, and then do a little scale by 0.1 of p of x going up the side, and that's a quick sketch of what that would look like. Okay, notice that is not uniform. Okay, there's not really much to say about this distribution. Okay, well, that's how you would graph it. And then to find the mean, variance, and standard deviation of the distribution, well, the mean, remember, was the sum of x times p of x, which we already found was 1.7. The variance will be the sum of this last column. So add 0.289, 0.147, and so on. Add those up and you get 0.81. Okay, so that's sigma squared, which is the variance. And then square root of that, 0.9. Okay, so the standard deviation, sigma, is 0.9. Okay, so hopefully that isn't too crazy. Okay, the last thing we look at is something called expected value. Okay, the mean, okay, I'm looking right here. The mean of a discrete random variable is sometimes called its expected value. Okay, so an example, at a fair, 1,000 raffle tickets are sold for $3 each. The 4 prizes are $500, $400, $300, $150. If you buy one ticket, what is the expected value of your gain? Okay, so x is going to represent your gain. And then p of x will be the probability of that gain. So when you look at your gain, x, and the probability, p of x, of that gain, well, the first gain, well, you could win $500. Now, you got to be a little bit careful because if you win the $500 prize, you had to buy the ticket first. So that was $3. So that means your gain is $497. Okay, so $497. And the probability of that gain is, we're assuming there's one ticket of each winner. So that's 1 out of 1,000 tickets. Okay, and then the next one, $397, with similar reasoning. And then if you win the $300 ticket, you actually gain $297. And then $150 ticket, you gained $147 because you had to buy the $3 ticket, and so on. Okay, now, those are only if you won. Well, what if you lost? That means you lost $3, and there's 996 out of 1,000 probability that you lose if you buy one ticket, that you lose the $3. Okay, so when you do x times p of x, so we're going to take 497 times 1,000 times 1 over 1,000, 397 times 1 over 1,000, and so on. And then when you add those up, you get negative 1.65. Okay, which basically means you expect to gain negative $1.65 for every ticket you buy, which is basically saying you expect to lose $1.65 for every ticket you buy. Okay, so that's a quick example of discrete probability distributions